And an algorithmic counterpart to this is that I give you a fixed graph H. There exists a polynomial time algorithm to test whether you have that graph as a minor. So together, these two theorems imply that you can test for membership in any minor closed class in polynomial time. Right? So, of course, this algorithm is very non-constructive because we only know the excluded minors for a few minor closed classes of graphs. But what maybe isn't as widely known is that this algorithm itself is non-constructive because it depends on bounds that have been proven to exist, but we don't know what they are. Right? So I'll mention width, I guess, because this is a width meeting. So the beginning of this algorithm is to test if your graph has big tree width, and we know that some number that is big works, but we don't know what that number is, right? So this is what this talk is about, explicit bounds, so that you could actually program this algorithm if you wanted to. Okay, so it turns out that the main abstraction to get explicit bounds is topological, right? So I'm going to make some definitions by picture. So, I'll go here. So we have a surface with boundary. So this is a surface with boundary. These are holes, and that is a handle, and that is a crosscount. Right. So, and a pattern is just a set of points on the boundary of the surface. So this. And the pattern specifies how I want to connect up these points. So this means that I want to connect the vertices labeled 1 together with the vertices labeled 2 together. And I want to do these with paths, disjoint paths on the surface. Right? So I can do it like this, and that. That, say, goes through the cross cap. Maybe I'll go like that. So this collection of paths on the surface I call a linkage, and it is a pi linkage if it matches the pattern that I want. Right? So I've defined a pattern and a pi linkage, and yes, okay, that's all we need. So what we want to prove is that if I give you any pattern, and I give you a non-separating curve in the surface, then you can find a linkage that hits that curve only a few times. And this few number will be explicit as well, right? So write this down. So I've got a surface sigma, and I've got a pattern pi in sigma. And the pattern is feasible. So feasible just means that there is some linkage in the surface that links those points up. All right. So the theorem is that if I give you any non-separating boundary sigma path, this just means that it is a curve with both of its endpoints on the boundary, and it's otherwise disjoint from the boundary. And I want the endpoints of this path to be disjoint from my linkage vertices. So in this case, there is a linkage. Such that each path in the linkage only hits this curve P at most twice. Right? So linkage L. So it's interesting that this bound here actually doesn't depend on the genus, right? So, so that's all I know. And I think I have enough time to prove this theorem, hopefully. We'll see what happens. So basically the idea is to kind of do an induction on the topological complexity, right? So I'll say what I mean by that. So let's take a counter example. So I've got my surface sigma, some pattern pi, this path P. So this is a counterexample with the genus, the number of vertices in linkage vertices, and number of holes. So I take this to be lexicographically minimal. Okay, so that means this genus thing is, well, it's not the number of handles because this is for orientable. So it's 2 times the number of handles plus the number of crosscaps. And so any surface of lower genus but possibly more holes is less complex for me, right? So, okay, so. And let's let L be a pi linkage. Okay, so because we've chosen this counterexample kind of topologically minimal, we can say some things about the curves, right? So, okay. So the first observation is that no path in the linkage is contractible. Okay, so contractible means that, so here's a hole, and here is maybe some linkage path. And contractible means that, well, so I'm supposed to link those up. It just means probably what you think it means, that this region is a disk. One of these 2 regions is a disk, right? Okay, so the reason that, okay, so the claim is that no linkage path is contractible, and that's because, well, so if we've got a contractible path like this thing is planar inside, and so that means that there must be 2 linkage vertices that are consecutive along this hole that you want to link up, right? So maybe this 2 and this 2, right? And then what you can do is just delete that pair from the linkage thing, right? And apply induction, right? So you know that for the rest of the linkage vertices, you can find a linkage that doesn't meet P, because at most twice, and then you can just put this back in, right? So if you stay very close to this hole, you can make sure that you avoid this linkage that you found by induction, and that you'll hit P at most twice, right? So that's that thing. Okay, 9 minutes. Okay. Okay, the second thing. Okay, the second thing is that no linkage path connects up two different holes. Right, so. Okay, so why is that the case? So you've got, say, two holes, and you've got some L that, say, connects these things up. And say you've got your path P that does this. I should have used a different color. Okay, so, right, let's delete this. Let's try this. So this thing is P, right? And I've got this linkage path that connects up two different holes, like this, right? So, well, what we can do is, well, this curve P is non-separating, right, by hypothesis. So what I can do is, I can find a curve that connects these 2 points up that is disjoint from P, right? So, because this thing is non-separating. So in this picture, it looks like, let's go this way, under the handle, and like that, this L prime guy, right? And you might think that, so what I'm going to do is cut out L prime, right? But I have to make sure that the rest of I can still link up the rest of the linkage vertices, right? But basically these two curves are the same topologically, right? So when I cut open along this curve, all I do is I get the same surface, but these two holes become one. And the same thing is true when I cut open along this curve, right? So topologically these two curves are the same. So if this is that means that I'm still feasible after cutting out along this curve, right? So I cut along this curve, I still have a feasible pattern, and then I just apply induction, and I'm done. All right, so let's do 6 minutes. Okay, so so for similar reasons, P is not contractible. And actually, this is by hypothesis, in fact, right? We assume that P is non-separating, right? So it's not contractible. But for inductive purposes, it's useful to have this, that when P is not contractible, right? And also, the ends of P are on the same hole. Okay, good. All right, so now 5, right? So now we know that there is some hole that contains both endpoints of P, right? So so this hole H H I claim must at least contain another linkage vertex, right? So okay, so why is that the case? Okay, so I have this hole. It contains the endpoints of P. Maybe something like that. And now I've got, say, another hole here. And I've got some linkage things, 3, 2, 2, so forth, and P, right? Okay, so if this is, so this is the hole that P is on. If it doesn't contain any linkage vertices, right, then what I can do is I can just find a curve that is connecting up this hole to this hole, let's say. Right. And this curve is disjoint from all the linkage vertices. And so I just cut open the surface along this hole, right? So what I do is I reduce the number of holes by 1, right? And actually these two holes become a single hole, right? But the relative position of these points doesn't change in this bigger hole, right? And all that's happened is there's one fewer hole, right? So after I cut open along this curve here, the pattern is still realizable in the surface with one fewer hole, right? And so I just apply induction and I win, right? So I know that there actually is, there are some linkage vertices on this hole here. Okay. So let's say, got some points here. 4, 4, 5, 5. So what I want to do is I want to take a point that is adjacent along this hole to one of the endpoints of P. Right? So I just take one of these guys, and there is some curve here. Right? So you have some curve, maybe that connects these things up. I'll draw into like that. Okay. And so now what we do is, okay, so now we just look at this geometric intersection of this curve and P, right? So the geometric intersection is the intersection number between P and all curves that have the same type as this thing, right? So the minimum over all curves of the same type, right? And so in fact, whenever you have two curves like this, right, it depends whether this curve is separating or not, right? So for the moment, let's assume that it's non-separating, right? So if it's non-separating, then actually this geometric intersection number is at most 1, right? So if you have two curves on the same hole, both of which are non-separating, then you can always replace this curve with one of the same type, such that I only meet P once, right? So that's what I'll do. I'll replace this curve by something that intersects P at most once, right? And then I'll cut the surface open along that new curve, right? By the same reasoning, the linkage will still, the rest of the linkage vertices will still be realizable because the two curves are the same type. And what's going to happen is, well, there are cases, right? But basically, if this curve is, say, two-sided, then I will get two holes in place of one hole, right? And so, let's say, so if the curve that I cut out on is, say, two-sided, then this one hole basically becomes two holes, and the genus is reduced, right? And unfortunately, we get sort of two copies of P, right? So there's a portion of P that will be on, say, one hole, and a portion of P that's on the other hole. So maybe a P1 and a P2, right? But the point, so now we're in trouble because we have two curves, and I want to apply induction, actually, right? But what you can do is you can apply induction on the non-trivial part of P after you cut it out, right? So you apply induction here, and you win by this, so you get something that meets P2, each curve meets P2 at most twice, but then you've got this P1 thing to deal with, right? But here's where choosing this thing to be adjacent to P was helpful, right? So you choose it to be adjacent to P, and moreover, you can choose it so that this curve that you get actually bounds a disk. So that's a disk, right? And so because these things are consecutive along this hole here, there's no reason that this linkage needs to intersect this part here, right? So it could intersect this part, but you just perturb it so that it doesn't, right? Okay, so I might have been ambitious that I could finish in time. So I'll just end by saying that this silly theorem, with it you can actually get explicit bounds for redundant vertices on a surface, right? So if you have, so one of the things you need to do in this minor testing algorithm is to find redundant vertices on a surface, and there's this notion of protected vertex, right? So you've got a vertex that has a lot of cycles that surround it, the bound disk, you know you can safely delete it. And this theorem gives you how many of those cycles you need. So I should stop right here. I should stop. Okay. Okay. There might be questions.
Okay. Thank you very much.